Hello everybody, my name is Ferreira. I'm a PhD student from Brandenburg University of Technology and a fellow of the Rescue European Training Network. Today, I present you the work Real-Time Dynamic Hardware Reconfiguration for Processors with Redundant Functional Units. So today we have this electronic scaling and the integration rate of these electronics as well going pretty high. At the same time, we have this increased amount of smart devices like multi-purpose device, multitasks, and so on, and the incredible strive for performance, not only anymore in the mundane applications like smartphones, but also for aerospace and automotive industry as well, which is highly critical application domain. In this work, we focus in mixed criticality scenarios, and our target is to minimize fault effects using redundancy in processor functional units, finding a compromise between full core and partial replication. Not only that, we want to provide on-demand reconfiguration capability, so we can minimize aging of electronics and save some power by not using all replicated units all the time. In the next slides, I'm going to present you a platform to enable modular redundancy on demand, combining controllable fine-grained replication of functional units and software-based dynamic reconfiguration strategies. We then build our prototype for the configurable processor design. Based on Plasma processor, we basically triplicate the functional units to enable double or triple modular redundancy. We extended the instruction decoder, adding new opcodes to control the reconfiguration and read from some fault counters to keep track of the detected faults in the design. We also equipped each functional unit with a Muller C element plus a delay line to filter small glitches in the logic. Finally, we add a volter to enable fault detection when in DMR and fault correction when in TMR configuration. Additionally, we extended an operating system to be able to control this processor design and the reconfiguration mechanism. More specifically, we extended the process data structures to attribute a criticality parameter to each process and the process switching mechanism to enable units reconfiguration at process switching time. As a result, we can deterministically perform design reconfiguration in runtime and program the hardware on demand either for fault tolerance mode or for aging avoidance mode. Such a reconfigurable platform can provide not only increased fault tolerance using TMR scheme for high critical process, but also power and age minimization using single units execution when no criticality is involved. Additionally, we can implement software approaches for reaction on fault detection. For example, branch on fault, interrupt on fault, and trap on fault. Once implemented, measures like instruction re-execution can be performed, selecting the same unit, different one, or simple enabling TMR for the re-execution. To evaluate our prototype, we first measured the latest incurred over the process switching mechanism, which gave us an increase in 5.1% on its execution time. Concerning hardware overhead, the original processor design has 60% of its area covered by the functional units, so an overhead of 120 is incurred to triplicate it. Also, an additional 18% of area is incurred for the combination logic to control the reconfiguration itself. For the fault tolerance, there is a TMR configuration. However, comprehensive fault injection campaigns are still to be done. Finally, we evaluate the impact of the real-time characteristics of the system. At first, checking the execution time overhead incurred by the mechanism, we could see that it's very deterministic. So, there is no effect of the real-time determinism. Secondly, although the fault correction on fault detection strategies are meant to be used for mid-critical process, a major study on its impact over the execution time and process deadlines is a work in progress. To conclude, I presented you a platform to cope with mixed critical scenarios. It configures itself on demand to provide fault tolerance or age minimization at a cost of an overhead of 5% in the execution time of the process switching mechanism. Although not negligible, our hardware overhead still below full core replication approach for fault tolerance, such as core lockstep schemes. These are some references, and thank you for your attention.